Welcome back to differential equations. In this video, I'm going to be talking about reduction of order, which is a very effective but incredibly situational change of variables techniques for dealing with second order and higher order differential equations. In these situations, I'm going to assume, first of all, that we have a linear homogeneous ordinary differential equation. I'll deal with a second order equation. So we have A times y double prime plus B times y prime plus C times y is equal to 0, where A, B, and C could be constants, but most likely are functions. If they were constants, we could use the method of characteristics. There wouldn't be a lot going on here. And assume that somehow we have been delivered that y equals f of t is a solution to this differential equation. Now, this is a second order differential equation, and we know that the general solution to a second order differential equation is going to involve two linearly independent solutions. So now that we have one, we need a second. And the key of reduction of order is to look for a second linearly independent solution, which is going to be in the form y equals some u of t times f of t. And if we differentiate, remember here that u and f are both functions of t. I'm going to suppress all of the of t's because this gets really messy really quickly, and the less we write, the better off we're going to be. But u prime is going to be derivative of the first times the second plus the first times the derivative of the second. And then y double prime is going to be, well, use the product rule on u prime f, then use the product rule on u f prime. And I guess we can combine some like terms here. U double prime f plus 2 u prime f prime plus u f double prime. Then substituting all of these things into my differential equation, and this is why suppressing all of the of t's was so important, because this is going to be a tight fit on the screen as it is. We have a times u double prime f plus 2 u prime f prime plus u f double prime plus b times y prime, which is u prime f plus u f prime plus c times y, which is u f equals 0. Distribute everything. And then the reason that this is going to work out so nicely for us, I want to get all of the terms that have u rather than a derivative of u together. In fact, I'll get all of the u derivatives together. A f u double prime 2af prime plus bf u prime and a f double prime plus b f prime plus c f times u is equal to 0. A couple of things to keep in mind here. The first one, a, b, c, and f prime and f double prime are all known functions. These are all things that we know going into the scenario. Another thing, and the more important thing to keep in mind, is that f is a solution to the differential equation. A solution to the differential equation literally means that a f double prime plus b f prime plus c f is equal to 0, right? This thing that I underlined in blue is the left-hand side of the differential equation if you plug in y equals f. And the right-hand side of the differential equation says that that must be 0. And so we have turned this into a differential equation that has u double prime and u prime, but not u itself. We dealt with an equation that had this kind of form in the first video on change of variables. I've already used u, so I need something else. I'm going to use the Greek letter phi. Let phi of t equal u prime of t. Then I have af times phi prime plus 2af prime plus bf times phi is equal to 0. And again, remember that a and b are given to us in the differential equation. And we are assuming that the solution f is already known to us. So all of these things are known. We can solve for phi and notice that this is a first order separable ODE. I'm going to give us a very simple example. Y double prime plus 4y prime plus 4y equals 0. This is a second order linear homogeneous ordinary differential equation with constant coefficients. So we can solve this using the method of characteristics. Xc squared plus 4 times xc plus 4 is equal to 0. And notice that that is a perfect square trinomial. This is xc plus 2, the whole thing squared. We have a repeated root. And I showed you when we were talking about the method of characteristics how to deal with the situation of a repeated root. And I said that at some point later in the course, I would show you where that extra thing came from. Welcome to some point later in the course. We know that f of t equal e to the negative 2t is a solution. We want a second linearly independent solution. So I'm going to assume that there is an linearly independent solution in the form of some u of t times e to the negative 2t. I assume that it exists. And if I differentiate and I substitute into this equation, all right, y is u times e to the negative 2t. So y prime is u prime times e to the negative 2t. I guess it'll be minus 2 times u times e to the negative 2t. And y double prime will be u double prime times e to the negative 2t minus 2u prime e to the negative 2t. That's the derivative of u prime e to the negative 2t. Then I need the derivative of negative 2 u e to the negative 2t, which will give me a negative 2 u prime e to the negative 2t, and a negative of a negative, which is positive 4 u e to the negative 2t. Combining some like terms there. And actually, let's factor out, I'll do it in 2 steps. But if I factor out the e to the negative 2t, my life is going to be a lot easier. And I'm actually going to do the same thing up here on y prime. If I write that as u prime minus 2u all times e to the negative 2t, that's going to make my life easier when I perform my substitution, because I'm going to have y double prime plus 4 times y prime plus 4 times y. And I can divide both sides of this equation by e to the negative 2t, and all those things are going to go away. Factoring doesn't really help all that much except to compress all this so it all fits on one line. And I've got u double prime minus 4u prime plus 4u plus 4u prime minus, I guess it's going to be minus 8u, and plus 4u is equal to 0. Combine some like terms. I've got u double prime. I've got minus 4u prime and plus 4u prime, which go away. I've got 4u minus 8u and another 4u, which all goes away. U double prime is equal to 0. I can solve this differential equation by directly integrating. U prime is going to be some constant. I'll call it C1. And u itself is going to be C1 times t plus some other constant, C2, just directly integrating. And if we pick C1 equals 1, C2 equals 0, then we get the solution y of t is equal to t times e to the negative 2t, which is the solution we used in the case of the repeated roots previously. All right, so you don't have to go through this in the case of constant coefficients with repeated roots, but I wanted to go through that to show you where it came from, to show you that it is just following the rules of differential equations, just introduced a little bit out of order. I'd like you to look at the differential equation t y double prime plus y prime is equal to 0. And there are several ways we could solve this particular equation. The way I want you to focus on is verify that y of t equals the natural log of t is a solution, and then use the process of reduction of order to find your second linearly independent solution. All right, take a few minutes to play around with that one. I'll see you in the next video.